Hi everyone, my name is Jean-Marie Voirin and I am a lecturer at the Exploration and Production Center of IFP School. In this session, I will present you the part of the reservoir engineering course devoted to recovery of oil and gas fields and associated production mechanisms, as highlighted on this chart. We will mainly talk about oil fields. However, most of the comments apply to gas reservoirs too. First, we will try to understand why oil is producing and what we call recovery factor. Then, we will review the different recovery stages: primary, secondary, and enhanced oil recovery. You have seen in previous section how an oil reservoir is formed during geological times, and you have seen the properties of the rock and fluids. This drawing of a simplified geological cross-section shows a series of porous and permeable rock layers extended from the surface to the location of the oil reservoir. They are overlaid with a sealing impermeable layer called the cap rock and underlaid with other rock layers of no interest here. Most of the porous and permeable layers are saturated with water. This is called an aquifer, except in the oil reservoir where oil is trapped. In this part, water was replaced by oil over geological times. Only unmovable water remains. The aquifer is or was connected in some way to the surface, as indicated by the blue arrow over a distance which may be large. Due to this link to the surface, the pore pressure in a reservoir is usually close to hydrostatic, meaning that it is equivalent to the pressure of a column of water extended from the surface to the reservoir depth. Oil is lighter than water. When a well is drilled to the oil reservoir, the pressure of the oil column is less than the reservoir pore pressure. This excess pressure at the wellhead allows the oil to flow naturally. The well production rate is a function of the pressure drawdown, which is the difference between the pressure at the bottom of the well and the reservoir pressure further from the well. It is also a function of the fluid ability to move through the reservoir to the well. As oil is removed, the reservoir pressure will start to drop, and progressively the rate will decrease due to the change in drawdown. The oil quantity that can be produced from a reservoir is called recovery. Initially, it depends on the natural energy present in the reservoir and how efficiently this energy is passed on to the producing wells. If natural energy is not sufficient to yield an economical combination of rate and recovery, external energy will have to be provided. This is the subject of this lecture. To easily compare the effectiveness of the different recovery methods within a given field and between fields, a dimensionless ratio is used. It is called the recovery factor and corresponds to the percentage of the volume of oil effectively produced or recovered from a reservoir as measured at the surface to the volume of original oil in place calculated in the same surface conditions. The recovery factor depends on a number of parameters, including the field rock and fluid characteristics, the production mechanisms and the associated recovery stages, natural energy only or supplemented by external energy, the number, type and location of wells, producers and injectors, and the production economic limit related to production level and associated costs. These different items are always interrelated. The oil reservoir is located at a depth that can reach a few kilometers. It usually has a length and width of several kilometers and a thickness of tens to hundreds of meters. Primary recovery corresponds to production mechanisms which only use the natural energy present in the reservoir. It usually happens first during the life of a field, hence its name. This stage is also called natural drainage. Recovery can be increased by pumping the producing wells when needed. Even so, recovery at this stage is usually low, and an oil reservoir will often be produced by means of several producing mechanisms over its lifetime. The most simple case, which is also the most unfavorable, happens when the link with the aquifer is extremely weak or non-existent, and when there is no free gas in the reservoir. The only energy available is the energy associated with the compression of the oil, the associated unmovable water, and the rock. Prior to any production, the reservoir pore volume is filled by oil and unmovable water. The bars on the right represent the relative volumes of fluids in place at the initial pressure. When oil is removed from the reservoir by the producing wells, pressure decreases and energy associated with the rock and fluid compression is released. Several things take place. There is less oil, but the remaining oil has expanded due to the lower pressure. The space left is filled by the water, which expands due to the decompression and occupies a larger volume in the pores. The arrangement of the rock grains, which is modified, shrinking the pore volume available between them. Production has been made possible by the fluid expansion and pore volume shrinkage, replacing the produced oil. This production mechanism always exists as soon as the pressure drops in a reservoir. Depending on rock and fluid characteristics, the amount of producible oil will vary. To estimate how much oil can be recovered, a material balance of the reservoir system before and after production can be done. In this particular case, it results in the equation shown here. The oil volume, originally in place at the initial pressure, is on the left-hand side of the equation, whereas the right-hand side reflects the oil volume remaining at a later time at a lower pressure P, as well as the changes associated with water expansion and pore volume shrinkage. This material balance equation can be rearranged to show the recovery factor, the ratio of the oil effectively produced, called NP, to the volume of original oil in place expressed in surface conditions, called N. In this primary recovery case, with no aquifer and no free gas, the natural energy available is limited, as compressibilities of the oil, water, and rock are very small. The corresponding recovery factor is low. When inserting typical values in the material balance formula, the calculation gives a result of around 5%, means that 95% of the oil will be left in the ground. In a gas reservoir, however, as gas compressibility is much larger than that of the water and rock, primary recovery is the main production mechanism and may lead to high recoveries, around 80%. In oil reservoirs, too, favorable cases exist for which additional natural energy is present, leading to significantly higher recoveries. As you know, below a certain pressure, solution gas will be released from the oil and due to its high compressibility will provide additional energy by expansion. This primary mechanism is called solution gas drive. The recovery factor may rise up to 15%. A gas cap may also be present. As pressure drops due to the production, the gas cap will provide additional energy and displace the oil as it expands downwards due to the high compressibility and low density of the gas. This primary mechanism is called gas cap drive. Recovery by this mechanism depends on the ratio between the gas cap and oil volumes. A gas cap of large volume can lead to recoveries up to 40%. Often, the presence of an aquifer connected to the oil reservoir will provide energy and reduce the pressure drop as water replaces the produced oil. This mechanism is called water drive. The aquifer can be located at the bottom of the oil reservoir or at the edge. An aquifer is said to be active if it provides enough energy to efficiently replace the produced oil volume. To achieve that, the connection with the oil reservoir has to be good, especially in terms of permeability, and the size of the aquifer has to be large when compared to the oil reservoir volume. The active water drive is the most favorable case of primary recovery and may lead to a recovery factor of more than 50%, sometimes as high as 70%. Combination of these mechanisms may also take place in the same reservoir. However, most often, natural energy provided by the different primary mechanisms is limited and recovery remains low. When the natural energy contained in the reservoir is not sufficient to provide a reasonable and economical recovery, additional energy will have to be brought in by injecting fluids. These production methods are called secondary recovery methods as they take place following primary recovery. Objectives of the secondary recovery methods are to increase recovery by maintaining the reservoir pressure or at least limiting its decline, sweeping the oil towards the producers. The secondary recovery methods try to mimic nature and use specific wells to inject either gas, the same idea as gas cap drive, or water. This technique is called water flooding, and the idea comes from the natural water drive. It is the most common method as water is easily available at low cost. We will look at this in more detail in the following slides. In some fields, both fluids can be injected in different parts of the reservoir. Water flooding uses specific wells in addition to the producers to inject the water. When a water flood is initiated, water can be injected to supplement an existing aquifer at the periphery of the oil reservoir. This is called peripheral injection. In some cases, it is sufficient. If not, water can also be injected into the oil zone either at the start or progressively, following peripheral injection. This is called infill injection. In both cases, the purpose of injecting water is to sweep the oil towards the low-pressure areas created by the production. Water will replace the produced oil and limit further pressure drop. Now we will look at the level of recovery that can be achieved by this technique. This 3D drawing represents a segment of a regular pattern of wells in an oil field under a water flood, 3 producers and 1 injector. It shows what happens as water is injected into the oil reservoir. A part of the volume between the injector and the producer is not contacted by the injected water. It is colored in green. Sweeping of the oil is limited both horizontally and vertically. The efficiency of the sweep varies based on the level of heterogeneities and layering, high permeability layers being invaded by water more quickly, the water and oil relative mobilities. If water is significantly more mobile than the oil viscosity larger than water viscosity, the volume swept is likely to be small as water will channel through the oil. The well location, density, and the types of well drains, vertical, horizontal, and finally, the economic criteria which will control the cumulative injected quantities and final oil rate. The most accurate way to estimate sweep efficiency and assess the associated uncertainties is by using a numerical simulation model of the reservoir. Typically, 70 to 80% of the pore volume is effectively swept when combining all these elements. In addition, in areas effectively swept by water, there is still oil trapped in the pores due to strong capillary forces. Trapped oil is measured in the lab on rock core samples. This has a significant degree of uncertainty as the sampling is limited and the reservoir rocks heterogeneous. On average, only 60% to 70% of the oil can be mobilized and displaced. The remaining 30 to 40% is definitively lost for water flood recovery. When combining these effects and taking into account the fact that some compartment of the field may not be drained by any well, the recovery factor achieved by water flooding ranges from 35 to 50%. It means that more than 50% of the oil in place will still remain in the ground. Only the implementation of special processes called enhanced oil recovery, or EOR, will, in some instances, be applicable to significantly increase the recovery factor by another step. When EOR follows secondary recovery, it can be called tertiary recovery. However, EOR may have to be implemented initially, as in bitumen reservoirs, or after primary recovery, when water or gas injections are not an option. These techniques are more expensive and more difficult to implement, and their applicability is really field-specific, as they depend strongly on rock and fluid properties. As a consequence, their contribution to the total world oil production is less than 5% today. To achieve their objectives, these processes may modify the fluid mobilities to improve the sweep efficiency by adding polymers to the injected water in order to increase its viscosity and make it closer to the oil viscosity, or by heating the oil, usually using steam. Or they may change the capillary properties to mobilize the oil trapped in pores after water flood by adding surface-active agents, surfactants, to the injected water to strongly decrease capillary forces, or injecting solvents miscible with the oil as hydrocarbon gases, CO2 or nitrogen. To summarize this lecture, we will look at the typical field production profile with time. Production in ordinate, years in abscissa. It starts by primary recovery or natural drainage. The natural energy present in the reservoir is used for production. As available energy declines, so does the oil rate. The area below the curve shows what would be the recovery if nothing else was done. To increase recovery and maintain the oil production at a given plateau, secondary recovery methods have to be implemented at a certain time. Water has to be injected to maintain the pressure and sweep the oil towards the producers. As water starts to be produced, the oil rate will decline and other techniques may be needed, at least to limit the decline. These techniques may correspond to improvements of the secondary phase, for example, horizontal versus vertical wells, or enhanced methods, the enhanced oil recovery technique discussed earlier. This is the end of my lecture. I hope you found it interesting. Thank you for your attention and enjoy the rest of this online course.